let us continue with general topology. First, a warning, okay? This section, the whole section I.3, okay, this one here, about general topology, it's optional. The whole section is optional, so if you want, you can as well move forward in the video and start again in section 1I.4, okay, which is not optional anymore. But this section, which is optional then, is really to help you understand what is topology in a very general and very formal, at a very formal level, okay? But, and you'll see that there are beautiful insights about what the general topology is, so I will describe this right away. But then this, I think I do present this, otherwise it, unless, I mean, despite the fact that it's optional, I do present this section because it's nice to have this picture of the definition of a topology of continuity in a general topological space. You will see that it's very similar to measurable to the definition of sigma algebra that we will see later, which would be a very important concept in this course. So it looks a lot, and there are lots of similarities with the concept of sigma algebras and measurability of functions. That's mostly the reason why I do this. I present to you this section, although everything that is in this section is, so to speak, non-examinable. So back to the general definition of a topology. You see here, so warning, okay, first important thing, I no longer assume that I have a distance, okay? I'm in a set, E, without a distance, and I will call a topology a family of subset of E that satisfies the three axioms O1, O2, and O3, right? The first one that I want is that my topology, so remember, a topology is a family of subsets of E, okay? So I want this family that I call capital T. I want this family to contain the empty set and capital E. Second axiom, I want that if A and B are in T, then their intersection is also in T. And the third thing I ask topology to verify is that for any family, okay, there's really any family of sets in T, their union must also be in T. So that should remind you very much of something, okay? If you think about what we did in metric spaces, we defined what is the distance, and then we defined open balls, and then we defined open sets, and finally we verified that was a proposition, that was a consequence of the definitions, of these three definitions, that open set verified these three properties, that the empty set and E are in T, that they are open, we said they were open, that any two open sets, okay, their intersection is still open, and then the third property is that any union of open set is still an open set. Well, here it's no longer a consequence of other definitions, it's really our definition of a topology, and the sets of the topology T are called the open sets now. Okay, so you see, really, it's a change. You completely change your point of view on the problem, and you start from these three properties to define open sets. Okay, and the set of all open sets is called the topology. So when you have a set E with a topology T, we call this a topological space. So let me give you very simple examples, abstract examples, then I will come to more. Actually, we will then move back to metric spaces, but some abstract examples. So let E be any set, okay? E, if I take, for instance, T to be the empty set, so the set that contains the empty set and E, okay? This is what we call the trivial topology. So you can verify that T is a topology, okay? And in that case, that means the only open sets in E are the empty set and E itself. So that's the trivial topology. That's the first example. Let me give you another example. I can choose all the subsets of E. So I will use this notation from now on, and you'll see a lot later. P of E is the set of all subsets of E. Okay. all subsets of E. And this is also a topology, which we call the discrete topology. Well, this is not a very interesting, both of them are not really interesting topologies in general, because in the first one there are too little open sets, and in the second one everything is open, so it's not very interesting either. So you can imagine I can define the discrete topology in R. That would mean that any subset of R is an open set. This works, but this is not the usual, what we call the usual topology. Fine. So again, a closed set is just the complement of an open set. Okay, this is this definition here. And you can verify, I will not do it for obvious reasons, and it's not very difficult. So the closed set verifies these three properties, that the empty set and E are closed, that if the union of two sets is closed, and that the intersection of any number of sets is closed as well. I can define neighborhoods in general topology. In fact, the definition of neighborhoods that we've seen before, it applies right away. You only need to have open sets, and open sets are provided by the topology, so you can define neighborhood just as we did before. One important thing to ask, and you don't have to ask for it, but it's very nasty when you don't have this property, is to ask the topology to separate points. Just as we defined, there was this axiom in the definition of a distance, that it separates points. Here we ask for a similar property, but only using open sets. Or neighborhoods, it's the same. I mean, it's not, neighborhoods and open sets are not the same, but we can have the same kind of definition with open sets. So a topological space is Hausdorff. We say it's Hausdorff. If for any 2 points, which are different in your set, you can always find a neighborhood of the first one, which does not intersect and you can find another neighborhood of the second point, and the two neighborhoods do not intersect. Okay, so that's being Hausdorff. That's very important, for instance, when you're dealing with limits, because if you're not separated, you can find sequences which converge to two different limits. That's a mess. So in all of the time we will ask our spaces to be Hausdorff. Note that in a metric space, the usual, what we will call the usual topology in your metric space is the set of union of all open balls of your sets. Okay, so exercise. Okay, verify that this set, okay, exercise, verify that this set is a topology. Okay, this is a formal exercise, and it's called a topology induced by the distance d. Right? You can verify that this topology is Hausdorff, okay, because the distance actually comes from the fact that the distance separates points. Okay, and now let's talk. So it was just a small apartheid concerning metric spaces. So let's be back to general topological spaces. We can define, since we have open sets, we can define limits. Right? We can define limits. Since we have limits, then we will be able to define continuity of functions. So first, start with the limit of sequences, as we did before. So the sequence UN will say that it converges to some point L in my topological space E, if for any neighborhood of this limit, there exists a rank n large enough such that for any n larger than capital N, UN is in the neighborhood of L. Okay, so this is exactly, we already gave this definition earlier in metric spaces. And then for limits of function, well, it's exactly the same as before again. For any v in the neighborhood of L, there exists a neighborhood of A such that the image of the neighborhood of U is included in the neighborhood of V, which is the neighborhood of L. Okay, and if you can remember two things about this section about general topology, it's the definition of a topology, which you will compare. I suggest that you compare later to the definition of a sigma algebra in measure theory. And there is this theorem which characterizes continuity of functions. So not continuity at one point, but continuity everywhere in my topological space. And this very much looks like the definition of measurability of functions that we will see later. So we say, and I will not prove this result, I will give you for completeness, I will give you the proof in the next slide, but I will not prove it, I will not take the time to prove it. So if you look at this, well, so you have a function from a topological space E to another topological space F. And we will say that, it's not we will say, but given the definition of continuity that we had before, F is continuous on E, okay, on the entire space. That means it's continuous at each point. If and only if the preimage of any open subset of F, okay, so you take any element in TF, okay, and its preimage must be a subset of E. Okay, remember that the definition of this thing here, f minus 1 of V, okay, by definition, this is the sets of the set, yes, of all points x in E, such that f of x belongs to V. Okay, and what you ask is that f minus 1 of V, this set, defined like this, is an open set, so it is in the topology of E, right? So the proof is here, but I will neither comment on it or go into more details. Now, compactness, just a word about this. Again, this is really an overview and not, I don't want to be too specific about this. More generally, we have the Borel, more generally compared to Bolzano-Weierstrass, actually, I will come to that. But we have the Borel, what we call the Borel-Lebesgue property. So again, you start with a topological space, and we will say that a subset A of E satisfies the Borel-Lebesgue property if you look at any cover of A, so any cover by open sets. Okay, so that means that basically you take open sets and you use all this open set to cover A. Okay, so you have this inclusion. And A will satisfy the Borel-Lebesgue property if you can extract a finite subcover. Okay, so that means that you can find J here, which is finite, such that A is still included in the union of the AJ, so the union of this open set here, but J now is finite. So somehow, again, it relates to what I said before, that compact sets are relatively small. Okay, you can try this property say, in R or in RG. So you take the whole space, R, for instance, or an unbounded subset, and you can check that it's not compact with the usual topology. Okay, that means with the usual balls or intervals that you are aware of. Okay, you can check that the fact that being unbounded prevents from finding a finite subcover, so it prevents from verifying the Borel-Lebesgue property, right? And what we call a compact set now is a subset K in a topological space that verifies the Borel-Lebesgue property, right? And again, something that is not proven is that the Borel-Lebesgue property, let me call it just BL, implies the Bolzano-Weierstrass property. Okay, but in fact, and this is completely unproven. I'm not proving it. But in fact, what happens is that in metric spaces, so again, coming back a little bit to metric spaces, so I choose a metric space with the topology induced by the distance. Then the two properties, Bolzano-Weierstrass and Borel-Lebesgue, are equivalent. So you don't need really to worry about which definition of compactness that you choose. In general, you will work in metric spaces, so you don't have to worry too much about this. And you can find a proof here in this book. It's an old book. So now The last section of this first lecture is about normed vector spaces. So this section now is very important. And first we will define what is a norm. So far, bear in mind that there was no notion of vector spaces, so we never asked for the space that we have encountered before to be vector spaces. Now this is the case. So more precisely, I asked for E to be an R or a C, or so real vector space or a complex vector space, either one or the other, doesn't matter. And what I call a norm is a mapping from this space, this vector space E, to R plus. Okay, again, this is important. This is R plus and not just R or R bar. And it is a mapping that satisfies these three properties. First, the separation again. So if the norm, so if n of x is 0, then x must be 0 itself. Somehow the norm will be seen to measure the distance between 0 and the vector x in space. So the separation, then we ask for the norm to be homogeneous. So this is this property here that for any lambda in K, so whether it's real or complex, the norm of lambda times x, okay, which here it's a multiplication by a scalar, okay, the norm of lambda times x is the absolute value, or the modulus, if you prefer, of lambda times n of x. It's the homogeneity. And again, the triangle inequality, which reads here like that. Okay. So a normed vector space will be, it's a pair, it's a couple of two things. First, a vector space E and a norm N, such as defined in definition 1.4.1. What we will use most frequently as a notation for N of X is something like that. Okay, double bar X, double bar, and we can, if there is some doubt in which space we are working with, we can add E here to mention that this is a norm related to E. Maybe there are other norms, other spaces. So it can be good to mention that here, or just double bar X double bar and nothing here if the context is clear enough. What happens is, so now let's start with a normed vector space E here. What happens is I can define now a distance using the norm. And this distance is defined like that. Okay, for any two vectors x and y, I can define the norm of x minus y. And this thing here, this mapping, is a distance. So exercise, right? Exercise, verify that this is indeed a distance. Okay? And since you have a distance now, well, you have a topology. So you have everything. Everything that we've said in section 1.2 applies here to this distance. What can I say about distances? So this distance, just several properties like that that need not to be proven. The distance induced by the norm is translation invariant. So it's quite explicit. The set of all open balls is stable by homothetic transformation. Okay, so if you take all open balls that you translate it or dilate it, it's still the same. The set of all open balls remains equal to the set to the new set by transformed by homothetic transformation. The mapping X, which takes it to the norm of X, is Lipschitz continuous, and the Lipschitz constant is 1. Okay, that is a consequence of the triangle inequality. Okay, maybe I can write why this works here. So what you do is that X is equal to X minus Y plus Y, because these two just cancel, minus Y plus Y. And now I use the triangle inequality, which tells me that this is less than X minus Y plus Y. So if I read this differently, this means that X minus Y is less than the norm of X minus Y. Okay, and I also get that, and similarly y minus x is less than x minus y, right? So in the end I can just put the absolute value around norm of x minus norm of y, and I get this result, which is exactly the Lipschitz continuity of this mapping. Okay. Yeah, and finally, just one more important definition here is that a complete norm vector space, so you have a distance, the one we discussed here, you can define Cauchy sequences, you can then assume that all Cauchy sequences converge, and a complete norm vector space is what we call a Banach space. Okay, so that will be very frequent vocabulary in the following. Perhaps let me give you some example. So first, notice that all norm vector spaces are Hausdorff. What else can I tell you? Yeah, maybe some examples. Example of norm vector spaces. So the first one that comes to mind maybe is RD with the Euclidean distance. Let's call it DE. Sorry, with a norm, Euclidean norm. Sorry. So we'll call it E for Euclidean. That is given like this, defined like this. The sum of xi squared from 1 to d. Okay, that's the Euclidean norm. Of course, you recover the Euclidean distance, but I could also have chosen, so maybe now if I want, I can choose this norm as well. And this norm is just, oops, sorry, like that. It's the sum of the xi from I equals 1 to d. You can check the homogeneity each time, the triangle inequality. Another one, which is this one, x infinity, here is the maximum between x1, x2, etc., xd. You can check that this is again a norm. What happens is, maybe you've heard about this before, that all norms on RD are equivalent. Meaning that, so let's say I have two norms. Okay, let's call them, so I've already used one. So, so let's call them N1 and N2, these two norms. That means that there exists some constant C, which is positive, such that for any x in RD, you will have the following, that 1 over C N1 of x is less than or equal to N2 of x, which is less than or equal to C times N1 of x. Okay? Right. So all norms are equivalent, so you will not prove this, although this is not a very difficult exercise. Let me give you some, so this is in the context of finite dimensional vector spaces. R is a finite dimensional vector space. You can replace R by C, and this is perfectly equivalent. Let me give you a little bit more involved example. Okay, let's consider the space of continuous function from, let's say, the interval 0, 1 with values in, here it doesn't matter, let's say R, it can be RD or whatever. Okay, and then I will use the norm. So if f is a continuous function, I will define the norm, the infinite norm of f, to be the supremum for all x in 0, 1 of the absolute value of f of x. Well, check that C0 R, this space of continuous functions with this norm. I mean, check that this is actually a norm. So check this is a normed vector space. But be careful. And I want you to think about why this space now, if I choose, for instance, the space, so this is still a vector space from R to R, all the continuous functions from R to R, but this with the infinite norm is not a norm vector space. And I want you to think about why this is not a norm vector space. Okay. One more thing perhaps that we will see in the following is that in finite dimensions, all linear mappings, okay, so let's say if I have a linear mapping from Rd to Rm, whatever D and M are finite, any linear mapping is continuous. Okay, and when I say continuous, I'm referring to the topology of Rd and Rm, which is the usual topology. So that's the topology of the norm. And since all norms are equivalent, I don't need to say precisely which norm I'm talking about. Okay, so in finite dimensions, linear mappings are all continuous. Okay, this is not at all the same in infinite dimension, and we'll see that later. So now let E and F be two norm vector spaces, and I will call, to be more precise now, I will call straight L of E and F the set of all F-valued linear mappings defined on E. And calligraphic L now is the same set of linear mapping, but with the condition that they are continuous. I'm asking them to be continuous now. And one more notation, which is quite usual, is to call E prime here what we call the topological dual of E. That's something that will come back a lot in the PDE class. E prime, which is a set of continuous linear mapping from E to K. So remember that K is either R, the field of real numbers, or C, the complex numbers. And now we want to characterize continuity of linear mappings, whatever the dimension of E or F is. Usually, I mean, I told you that if E is finite dimensional, all mappings are continuous. So what we have in mind really is that E and F are not finite dimensional. So we have the following characterization of continuity. For U, a linear mapping from E to F. So U is continuous on E, is equivalent to being continuous at only one point. I said 0 here, but it can be any point. Okay, so being continuous at some point is enough to characterize continuity everywhere, for a linear mapping, of course. Then it's also equivalent to being bounded on the closed unit ball. Okay, if U is bounded, if you take the supremum of U over all points, all vectors of the unit ball, then it's enough to characterize, it's enough to be bounded to characterize continuity. It's enough also to be bounded on the unit sphere. It's enough, or it's equivalent, actually it's stronger usually, to be Lipschitz continuous, or equivalently to verify this inequality, which says that U of X is always smaller than C times the norm of X for some constant C. It suffices that there exists some C here. So all these points are equivalent. Let me prove that. So we'll use a circular argument. Prove that 1 implies 2 implies 3 and so on. So 1 implies, remember, okay, 1 implies 2. This is quite obvious because if you are continuous everywhere, you're continuous at 0. So 1 implies 2 is okay. Now 2 implies 3. Well, remember what this is. So I'm assuming that U is continuous at 0, and I want to prove that U is bounded on a closed unit ball. So there exists, if U is continuous at 0, there exists alpha 0 positive, such that for any X in E, such that X is smaller than alpha 0, then this implies that U of X is smaller or equal to 1, say, because this is just continuity. I'm choosing instead of epsilon here, I'm just saying 1, because it doesn't matter. And if I do that, well, what does it mean? Remember what I want to prove. I want to prove that U is bounded on the closed unit ball. So that means for any x that the norm is less than 1. Well, okay, I will use this property. So let y be in the closed unit ball. Then alpha 0 y, sorry. Okay, alpha 0, yeah, I need a large inequality here. Okay, then alpha 0 y, so the norm of alpha 0 y is smaller than alpha 0 because the norm of y is smaller than 1. And so y is less than alpha 0. So the norm of u of y, okay, is equal to the norm of u of alpha 0 y over alpha 0, which by homogeneity, so alpha 0 is a positive number, so by homogeneity this is 1 over alpha 0 times the norm of u of alpha 0 y. Okay, and now I use the fact that the norm of alpha 0 y is less than alpha 0 and use the continuity of u to deduce that this is less than 1. So all this is less than 1 over alpha 0. Okay, so for what I proved is that for any y in B bar, the norm of u of y is smaller than 1 over alpha 0. Okay, so I have boundedness in the unit ball. The fact that 3, so boundedness over the unit ball implies the boundedness over the sphere is okay, it's obvious. Okay, it's just a subset of the unit ball. And now I want to prove that if I'm bounded on the unit sphere, then there exists constants such that u of x is smaller than cx. So I will not do the details, it's quite similar to what I've done here, the same kind of manipulations. So 4 implies 5 is exercise for you. 5 implies 6, it's only because of linearity. Okay, remember that 5 implies 6. This is just doing proving that u of x minus u of y is less than c times x minus y. This is just by linearity. And now the fact that u is Lipschitz continuous implies that it is continuous. This is always true. Okay, you can check that. Lipschitz continuity implies continuity. And we are done. So a few more comments on this. For the set of continuous linear mappings from E to F is a sub-vector space of the set of all linear mappings, calligraphic straight L, sorry. We can define a norm on linear mappings. So this is, like we said, this is a vector space here. Actually, this one rather is a vector space, and we can define a norm on this vector space, a new norm, which is called a subordinated norm usually, and it is given by, can be defined like this, like the supremum over the unit ball. So here B is the unit ball, the supremum of the F norm of u of x. Okay, and that you can check is again a norm. Any linear mapping defined on a finite dimensional space with values in any non-vector space F is continuous. That's what I mentioned earlier. You can try to verify this. And I will conclude with one more theorem that I will not prove, but that can be very useful. Actually, it will be useful later, in particular on Hilbert spaces during the next lecture. So let's define first an isometry. So let E and F be two norm vector spaces. And isometry is a linear mapping such that the norm is preserved. So it's given here, it's written here literally. For any x in E, the norm of the image is equal to X itself. That's an isometry. And a very nice theorem, which gives the existence of mappings on larger space. When sometimes you can prove or you can construct a mapping on rather small space, and under certain condition you are able to extend this mapping to larger spaces. That's something that we can do with, for instance, with Fourier series. We can start on small spaces and extend in Fourier transform. Actually, you can define it on a smaller space and extend it to a very large space or to a larger space. So that's something very useful that we will use really in this course. So let E be a Banach space. So this time I'm assuming that the function takes values in a complete space. It's important. I will assume that F is a dense subvector space of E, and that U is a mapping from F to E. Okay, the fact that F is dense in E is very important to be able to define properly the extension. And we will assume that U is continuous and linear. Then in that case, U extends uniquely to a continuous linear mapping that we call U tilde, okay, which is defined not only on F, but on the whole space E. Moreover, what we have is that if U was an isometry, and of course still, in fact, an isometry is continuous, so I do not have to say it again, but if U was defined as an isometry on F to E, then U tilde still has this property of being an isometry. So the proof is in this book by Reed and Simon, which is a very famous book in functional analysis, and the theorem is 1.7. And to conclude with this lecture, let me give you some references which I mentioned during the video. So the first one by Ramis Deschamps and Audoux, it's in French. It's an old book from class préparatoire. The book by Reed and Simon in functional analysis, which is a classic, and which is very nicely explained. And everything is quite nice and not too complicated. The book of Rudin is an absolute classic. It's in English, and it's called Real and Complex Analysis. It's a bit more elaborate than what we present here, but most of the results that we will discuss during this course are covered in this book, which focuses a lot on measure theory and complex analysis. Thank you very much, and see you for the next lecture.